learned how to graph sine and cosine graphs, particularly using that DAB-C method. Hopefully yesterday's activity was really good for you for practicing that and getting an idea of how that works. Now we're going to look at where do we have real-life situations where things repeat themselves, and how can we use sine and cosine graphs to help us model those equations and solve those equations. So sometimes we get a question where the model is already provided. So here's an example. Depth of water in a harbor is given by this equation. The reason this is as a sine and cos graph is because tides repeat themselves. The tide comes in, the tide goes out. The tide comes in, the tide goes out. And any process that repeats itself like this will be a sine or a cosine graph. So they've given us that equation, and part A, I'm going to just, we're going to sketch the graph. So again, this is a practice of using our DAB-C ability to draw this graph. And what we would do here, we would start with the D value. The D value is 13.7. So I mark somewhere 13.7. And I draw a dotted line at 13.7. I have now done the D part. A is our amplitude. We've got a negative 4.5, but amplitude is always positive, so this means we are going to go up 4.5. That would take me to 18.2, and down 4.5. That will take me to 9.2. And labeling the max and the min is what we have to do with our A value. Next is our period. Our period is always going to be 2 pi divided by our B value, and our B value is 0.16 pi. So I type that into my calculator. And I get 12.5. So somewhere along my x-axis, I mark 12.5. I divide that into 4 equal sections. Half of 12.5 is 6.25. Half of 6.25 is 3.125. And this would make this 9.375. So divide it into 4 equal sections. Next, we would draw the graph without a shift. I hope you notice, though, in this graph, there is no shift. So we don't have to do anything in this graph for a shift, so we can go directly to its graph. It is a negative cos graph. Negative cos graph would start at a minimum. Those minimum, center line, maximum, center line, minimum. And we've got our graph. Now, for part B of the question, part B says that this is a big ship, a bulk carrier, needs at least 14.5 meters of water in order to come into the dock safely. So sometimes with tides, you have problems because you bring your ship in, and if all the water goes out, you're going to either get stuck or going to be in a problem. So here, if we go back to our graph, and we label 14.5, and draw a dotted line at 14.5, can you see that it's only going to be deep enough in this yellow section? So we're going to see if we can find a way to solve for these 2 points. And we're going to do it with technology. So if you have a graphing calculator, you can take that out. If you don't have a graphing calculator, I'm going to get you to go to the internet, or there is an app on your phone that you could download called Desmos. It's like a graphing calculator for your phone, very useful, and we'll be using it in this class. So if you don't have a graphing calculator, I'd like you to get the app Desmos and add it on there. And what we're going to do is either in your graphing calculator or in Desmos, we're going to type in the equation. So the equation that we had was negative 4.5 cos of 0.16, and I believe there's a place where you can even yet click and have pi get added in. It has times t, but in the Desmos and the graphing calculator you can put x plus 13.7 and if you scroll out, you will get the exact same graph that we drew. Then in the second equation, we're going to type in y equals 14.5. That will draw a straight line. On the Desmos program, what we're looking for was this section here. And if you just go to the point, 3.48 and 9.02. So it's really quick on the Desmos program to find these times 3.48, because you just have to scroll over top of them, and 9.02. For those of you using a graphing calculator, I'll do it on the graphing calculator as well. On your graphing calculator, you're going to have to make sure that you are in radians. So you can do that by hitting your mode button and clicking on radians. On your graphing calculator as well, you are going to have to set up your window. So if we think about how we graphed our graph, if we look at it again here, the graph that we drew our x-axis went from 0 to 12.5, and our y-axis went from 0 to 20. So when I go to my graphing calculator, I tell my x-min, maybe I start -1 just so that I can see my axis, but I went to 12.5, so I'll go a little bit more to 15. Our x, our y-min, again, a -1. But here I'll go up to 20. You can even set your scale, like if I go 3.125, that's exactly the scale that I have. Now when I hit graph, oh, wait for it, am I in? I'm in radians. Oh, I have an extra 0. There, oh, that was not the right button. Okay, negative 4.5 cos 0.16 pi x, close my bracket, plus 13.7. And again, my graph looks and should look like this. On the graphing calculator, you would go to Y2, just like on Desmos, type in 14.5, and when you graph it, it draws that straight line. Now, the nice thing about Desmos is you could just hover over these points to find the answers. On the graphing calculator, you have to calculate where they intersect, and that can be done by pushing the second button, and above the trace button it says calculate, so second and trace. Number 5 is where they intersect. Push enter on the first curve, enter on the second curve, enter on the third curve, and here's the 9.02. It'll always find the intersection the closest to your cursor. So if I wanted to find the other one on my calculator, I'd calculate number 5 where they intersect, but now I would have to move my cursor if I'm closer to this one. Then when I push enter 3 times, it finds that one. Okay, questions about Desmos? Anybody having issues with it working? Yes? You're welcome. If you can't see it on your screen, just move your screen around, maybe you'll find it. And then you'd also type in the 14.5 in there as well. So if we go back to our notes, how many hours is that if we take 9.02 and minus 3.48? It is safe. For 5.54 hours. So if we have technology, we can solve questions like this very nice and very easily. That is a good thing to know how to use. Okay? If you go to university, they are going to probably not let you use your cell phone or your graphing calculator for a question like this. So then you would have to solve this with algebra. So we're not going to go over the algebra. I'll put it on, I'll show the algebra on the video just quickly. You can study it later if you want. What you would have to do is you would have to plug in the 14.5 for y and solve this equation. Step 1 would just be to get the cos by itself. And a strategy, because this is awkward with a whole bunch of stuff inside the cos, a strategy would be to temporarily just call the whole inside theta. So I do a substitution, I let theta equal the whole inside, and then I can find my reference angle and solve for theta in quadrant 2 and quadrant 3. And once you've solved for theta, then you would substitute back, and you could solve for the actual value of t either way. And you would get the exact same answers that we got with the calculator. Although the calculator is a lot nicer and a lot faster. Or Desmos, even better. So a lot of these word problems, what we have to be able to do is we have to be able to imagine the situation, draw the graph, come up with the equation. So here we have a question with a Ferris wheel. It has a radius of 15 meters and rotates once every 20 seconds. So I'm going to draw a little picture of a Ferris wheel. For those of you that don't know what a Ferris wheel is, it is a ride that goes around in a circle. It'll go. It has chairs. Woo-hoo. And you get on the ride. There we go. There you are. I'm so happy with your sitting on your chair, ready to go around. Oops, I didn't want to draw space. That's not good to decap. We gotta make sure there we go. All together. So much fun. And in 20 seconds, you go all the way around and have so much fun. So, we have to draw a graph of this situation. This is what's happening in real life. You're like, hopping onto the Ferris wheel. So, right beside this whole Ferris wheel, and try to draw it to scale here. Does it make sense that you would start right here at 1 meter above the ground? You can't get on a Ferris wheel halfway up, or they don't launch you and hope that you land on a chair at the top. That would be scary. They're like, okay, how much do you weigh? And we'll set this little launcher, and hopefully when you get at the top, just hang on to the chair when you land up there. It'll be perfect. That would be scary. It'd be kind of exciting. I bet you now I'm getting creative. I'm imagining if you figured out all the physics and mathematics correctly, you could launch a person up in the air so that they just softly land on the seat. If they plan it just perfectly, because gravity will slow you down and land. If you miss, gravity will speed you up and you'll hit the ground very fast. But if it was planned perfectly, we could probably create, I don't know, would the division allow us if we say we're going to do a physics activity with middle school? We get middle school kids, launch them into the air, learn by trial and error what's the exact amount that we need to launch them to land them perfectly on the chair. Probably not a good idea. Anyway, so it tells us also that in 20 seconds, so I mark 20 seconds along here, this will be time in seconds, well in 20 seconds we're going to be back all the way around. Here we are, got on 20 seconds, we're back to where we started from. So we could put another dot there. And if we imagine, where would you be then at 10 seconds? Does it make sense that at 10 seconds you would be at the top? Now, we have to imagine, where is that top? What number would I put there? How high above the ground would you be? Okay? So, what did the question tell us? A Ferris wheel has a radius of 15 meters. Radius is the distance from the center to the edge. We know that that's 15 meters. So how does that help me figure out that this needs to be 31? Does it make sense to you that if this is 15 meters, then that would be 15 there plus another 15? Our diameter would be 30. And if we started 1 meter above the ground, then our maximum would be 30 above that at 31. In fact, we can probably already see that the center line is going to be at 16. And what times will you be on that center line? Well, halfway of 10, that will be 5 and 15. It makes sense that that's where you would be on your center line. And this repeats itself over and over and over again. Of course, in real life, they have to keep stopping it to let people go on. But if you ever had the opportunity to be on a Ferris wheel for many, many minutes where they never stop it, then it would just continue in a graph like this. So, in my hometown of 1,600 people, every August they have a fair. And the town bought 2 rides probably 40 years ago, maybe 50 years ago. They have a Ferris wheel, and they have a ride that has chairs that spins around fast, and the chairs go out to the side and then come back in. Now, since the town bought these 2 rides, during the town fair, which happens every year, there are the same 2 rides for the last 50 years. As a result, if you love Ferris wheels, I'm going to tell you, you can get the best bang for your buck Ferris wheel ride at the Rostron Town and County Fair, because the fact that it's been there for 50 years, there's no lineup anymore. Everybody's like, yeah, I did that for the last 3 years, I don't need to. So I'm there, this is about 5 years ago, I'm back in my hometown for the fair, and I'm like, there's the Ferris wheel, so I tell my kids, I've got to take you on the Ferris wheel, because this is my hometown. We get there, nobody's in line, it's only like $1, so we pay the $1, get on the Ferris wheel, and we start going around. And about the 15th time that we're going around, we start to go, please, somebody get in line, because we're just going around and around, and they're not stopping it, and they're like, all right, you can have the longest Ferris wheel ride in your life, because there's nobody else waiting to get on. And you just kept going over and over and over again. So now we need to, with this, we took the picture, we drew the graph, and if we have the graph, we can think about DAB-C and see if we can figure out an equation. Can you see the center line from the equation? Yes. You know that your D value is 16. The amplitude is your A value. The amplitude is the distance from your center line to a maximum, center line to a minimum. Can we tell that from our equation? Absolutely. Your B value is related to your period. We have 2 formulas. We have the period formula. When you have the B value, your period is 2 pi over your B value. When you don't have your B value is 2 pi divided by your period. So in this case, we can tell that our period is 20 seconds. So our B value will be 2 pi over 20. And yes, you could reduce that to pi over 10, but actually, leaving it as 2 pi over 20 is a nice way of seeing the period in the equation. And we now want to find the equation. The C value is going to be different depending on what kind of equation you want to write. So, if you had this equation, I would say the most typical equation written from this one would be a negative cos graph. So a negative cos graph, well, your A is still 15 cos. Your B is 2 pi over 20. A negative cos graph is the most common because do you see there is no shift in a negative cos graph. So your starting point would be right here. And I'm going to draw a black dot for that spot. Then your D value is still plus 16. The second most common graph would be a cos graph, because it's really easy to find a maximum. So I drew a purple dot at the maximum. I'm going to draw a purple equation for this one. The amplitude is still 15. The period is still the same, so your B value stays the same. Your sinusoidal axis, or your center line, is still 16. What's different is our starting point. If you are making a cos graph starts at a maximum. That maximum has shifted 10 units to the right, so I write minus 10. also be quite common to draw a sine graph. If I wanted to draw a sine graph, I ask myself, where does a sine graph start? Sine graph starts in the middle going up, so I label that green dot. Because that green dot is in the middle where it's going up. I hope you start to realize that your A value, your B value, oh, this is sine graph now, sorry. Now we're doing a sine graph. Our B value, 2 pi over 20. Our D value, the dab part, stays the same no matter which graph you're using. It'll always have a 15, a 2 pi over 20, and a 16. The only thing that's changing is your starting point. This time we've moved 5 to the right. So for the green point, it would be x minus 5. And sometimes there's a negative in front, because if you did a negative cos graph or a negative sine graph, then your A value would have a negative in front of it. So we actually found 3 equations. How many would there be? A bunch more. Okay, part B of this question says, estimate the height after 22 seconds. So because it says estimate, you can just go to your graph, mark 22, go up to it, and over, and do an actual estimate. Okay? So if I was actually estimating, I'm going to say it's around 5 meters. If I wanted to find this exactly, I would have to use one of my equations. I could do technology, so I'm going to go back to Desmos here, and I'm going to type in this equation now. Negative 15 cos 2 pi divided by, oops, no, bracket 2 pi divided by 20, bracket, nope, don't need another bracket, x plus 16 and we have our graph. So if x is 22, I can just type in x is 22. We guessed it was 5. It's actually at 3.865. So we did an estimate of 5 looking at our graph. We could find it exactly using technology. You could also find it exactly with any calculator. All you would need to do is take this equation and where the x is, plug in a 22. And it would tell you what it is exactly. Next question says, estimate when you would be 20 meters above the ground. So I draw a horizontal line at 20. At 5.9 seconds, also at 14.1 seconds, you would be at 20. Now it says estimate, so if you were just estimating it, you would go back to your graph. You would draw a line at 20. And you would do an estimate where those points are. But if we wanted to find it exactly, we could use our graphing calculator or Desmos. How nice is that? It even finds the next times. And it keeps on going forever. The other nice thing about Desmos is zooming in and out and just moving it around is really easy. A little bit more complicated with your graphing calculator, because your graphing calculator, you have to set up your window so that you can see it. Okay. The most complicated graphing and word problems are probably ones that look like this. They're real life situations. They just give you 2 points, a maximum and a minimum, and a time. And the reason why this is a little bit complicated is because times don't happen in nice numbers. Like when someone says 430, should you put 4.3? No, 430 is halfway. So we have to figure out, okay, 430, I'm pretty sure you could figure out that you should label it as 4.5. But where do you label 1042? You're gonna have to figure that out. So, Bay of Fundy, highest tides in the world. Maximum depth of the water is 8 meters at 4:30 a.m. 6 hours and 12 minutes later, it has a minimum depth of 2 meters. So we know that our maximum is going to be at 8, our minimum at 2. I hope you can see that the center of that will be at 5. We know at 4:30, so I'm going to mark that as 4.5. At 4:30, it has a maximum depth of 8, so we have this point so far. And at 10:42, what decimal would I write for 42? How would you figure that out? Well, for 30, we figured it out that it was a half. Does it make sense that we figured out 30 was a half because 30 out of 60 minutes is 0.5? So if you did 42 out of 60 minutes, that reduces to 6 out of 10, 7 out of 10, because they both divide by 6. So you could change that to 0.7. So I'm going to go 6.2 hours later, which will be about there. I'll have 10.7, and that's when it is at a minimum of 2. And this is all the information that's given to you. So this question is more difficult because you have less information given to you, but because you know it's periodic, that it's going to look like a sine graph or a cosine graph, we can figure some other stuff out. For example, the distance between here and here is 6.2. That means if I go another 6.2 to 16.9, I will be back at my maximum. And in fact, I could label these marks in between, halfway and halfway. That's where I'd be on my center line. And now we've drawn one period of this graph. Do we have enough information for the dab? I think so. Can you see that your center line is 5? Your amplitude is 3. And our period, we have to figure out from our graph. If it's 6.2 from 4.5 to 10.7, it will be another 6.2 there, and our period will be 12.4. So our B value is always 2 pi divided by your period, will be 2 pi divided by 12.4. And now we have enough information to graph. We'll do one graph, I'll color code them. We'll do one graph as a cos graph. Where does a cos graph start? At a maximum. So my A value is 3 cos. My B value is 2 pi over 12.4. My D value is plus 5. So your A, your B, and your D value are not going to change. Our starting point, though, is 4.5 units to the right. So to shift something to the right, I'd have to do minus 4.5. For a sine graph, where does a sine graph start? In the middle going up. So you just need to find in the middle going up somewhere. Now we're going to have to figure out what that value is. Okay, if this is 6.2, half of 6.2 is 3.1. This will be 13.8. So for that purple point, as a sine graph, A value is the same, B value is the same, D value will be the same, but now we're shifting 13.8 to the right. Some people like to go, right, go backwards and find that point and use that one for your sine graph. You have options. There's more than one right answer when figuring these out. So we were able to graph the function, and now we found two equations. One with sine, and one with cosine. And then the next part says, estimate the depth of the water at 1:30 p.m. Okay, again, would it make sense to you that 1:30 p.m. would be at 13.5? It's 12 o'clock, 1 o'clock would be like at 13. So when we're using a numeric scale like this, we have to translate back and forth between what a time is and what the scale is we're using. And if I go up from here, maybe I think it looks like it's at 4. If I want to figure this out exactly, I'd have to go to my graphing calculator, type this equation in, my amplitude was 3. My shift was 4.5 to the right for my cos graph. And my d value is +5. There's my graph. We were finding it out at 1:30, so I go x equals 13.5. 4.5 is the actual answer. What did we estimate it as? Did we say 4 or 5? 4. Not bad. Pretty good estimate. I'm happy with that. Okay, so there are 2 questions there for you to try on your own. We're going to take the rest of class to work on some of these. Okay, you can ignore the homework that's listed at the bottom there, but I will give you some questions out of your textbook that you can do as well. So questions. In your textbook, you can circle on page 548, questions 3 to 9. So we did these questions instead of the questions in the notes. And then what I would suggest that you do, and I have tape up at the front, is when you get to 5.7 in your textbook, just take this paper after you've done the questions, because it's much easier to do the questions before you tape it in. But then just tape it to the edge. You can still flip it up, see behind there what it looks like. It folds nicely into your textbook exactly where we did this, so that you don't lose these notes.